Man, I can't wait to eat this Taco Bell that I've been looking forward to all day. I've been eating Taco Bell for the past 21 years for 3 meals a day, and it still tastes so good to me. Yeah. Oh. I'm feeling a lot of symptoms of heartburn in my chest, tightness, nausea, and or discomfort in my gastrointestinal and chest area. What's going on? It feels like my left side of my body is numb. I think I need help. Somebody call a doctor.
Dr. Alvin here. Well, kids, we could have seen this one coming. I told him to stop eating so much if he wanted to treat his atherosclerosis. It's the #1 killer in the United States, causing over more than 800,000 deaths a year. This form of cardiovascular disease is easily preventable by watching one's diet and lifestyle.
Atherosclerosis is the buildup of plaque, which includes fatty deposits, cholesterol, calcium, and other substances. Plaque eventually blocks blood flow through the arteries. Usually, when a material collides with an atherosclerotic lesion, it sticks to the plaque buildup already present and hardens over time. Atherosclerosis severely reduces the blood flow in an artery. The consequences can range from chest pains to strokes to heart attacks. The conservation of mass concepts have a real-life application in these cases. Biomedical engineers are able to develop a small mesh tube called a stent that is used to keep an artery open and allow blood to flow through at a normal rate. A stent is usually used after balloon angioplasty to ensure the artery does not close from the plaque buildup. Biomedical engineers can use conservation of mass concepts to calculate the radius of the stent needed, or can incorporate Newton's law of force and pressure to calculate certain parameters that the stent would need, like push force, stability, composition, stress and strain, etc. Now let's take a look at the problem statement. Fatty deposit covers the walls of a coronary artery, decreasing the vessel diameter by 75%. Our system boundary will be the plaque buildup site outlined by the dotted line, resulting in two mass flow rates, one coming into the system marked by M1 and the other traveling out of the system marked by M2. Let's look at this at a simpler manner. Our system can be represented by a simple box. Let's say a healthy patient has a blood velocity of 10 centimeters per second and an artery diameter of 4 millimeters, making its radius 2 millimeters. If the diameter is reduced by 75%, the radius of the outlet stream is now 0.25 times the radius of the inlet stream, which equals 0.5 millimeters. There are three assumptions that we can make from this problem statement. 1. The artery is a steady-state system. 2. There is no generation and consumption of blood in the system. And 3. We can treat the artery as a cylindrical system. Now, let's look at what is asked from us and what we know. We are asked to find the final blood velocity, and we know the initial blood velocity is 10 centimeters per second, the initial radius is 2 millimeters, and the final radius is 25% of the initial radius, equaling 0.5 millimeters. Now, let's look at some of the equations we will use to solve our conservation of mass problem. First, we use our generic mass accounting equation, in minus out plus generation minus consumption equals accumulation. 2. We will need the mass flow rate equation, m dot equals area times velocity times density. And finally, since the problem can be treated as a cylindrical system, the cross-sectional area is pi r squared.
To better understand this problem surrounding atherosclerosis, let's solve the problem together.
Now, we have all the information that we need to solve this problem. Using our generic equation and our assumptions, we can cancel out a few terms. The generation, consumption, and accumulation terms will equal 0. From this, we can infer mass flow in is equal to mass flow out. Then from equation 2, we know the mass flow rates equal area times velocity times density. We can cancel common terms and find that radius 1 squared times velocity 1 is equal to radius 2 squared times velocity 2. From this, we can solve velocity 2 to be radius 1 squared times velocity 1 all over radius 2 squared. So velocity 2 is equal to 10 centimeters per second multiplied by 2 millimeters squared divided by 0.5 millimeters squared, which is equal to 160 centimeters per second. Looking at the ratio between the initial and final velocity, we see the blood velocity for a patient with atherosclerosis, for this case, is 16 times the amount of a healthy patient. Without a stent, the heart would have to overexert itself to produce the final blood velocity. As a result, the heart could scar and eventually become permanently damaged and lead to death.
I should have listened to my doctor and listened when he told me not to eat so much in order to prevent myself from getting atherosclerosis. Now it's too late, and I could die.